Let me get started. Talk a little bit about, of course, all the production systems we're currently operating here at TACC. Start with, of course, our good old long-term system, Frontera. Been in production since July of 2019. Are y'all seeing the slides or?
Yes, we are.
Okay. I just want to make sure. It's been a great workhorse. I have to say it's already lived way longer than I had originally designed it for. And we're going to have to continue to operate it and probably until early 2026 timeframe, just because of the fact that Horizon won't be online until at least that timeframe. So we need to continue to support the community with Frontera. I'll spend some time on that, talk a little bit about the current configuration, give everybody an update, and then kind of the current challenges we still have on that one. And then I'll talk a little bit about Lone Star 6. Of course, that's the UT and TACC and UT system funded production system. That's our AMD-based system. And again, it's been in operation for a little over 3 years now. It's been very productive, and we're continuing to add and expand to it in terms of the design on it. Stampede 3 is the new big one. Of course, that entered production last year. That is a $10 million Dell system. We reused a bunch of the old Stampede 2 parts, still running OPA. We still have a bunch of our OPA fabric, and we do have plans to upgrade to OPA 400 later this year. And I keep referring to we, and that's not actually my problem, but it's the royal we at this point. So, and of course, Vista. Vista is our new NSF early access system, really as a test bed for LCCF deployment. It's our first foray into a fully ARM-based cluster. It's using the NVIDIA Grace Hopper platforms, the GH200 nodes. So far, we spent about $20 million total on that system. And again, I got a lot of good details on that and some early experiences and learnings on it since it's been in production for about 3 or 4 months now. So, of course, we're still operating our big 2 storage system. Stock Air 2 is our site-wide 10 petabyte file system. We mounted on all production systems. We figured out how to route it to Vista, Stampede 3. It's still a pretty good file system. We have struggled a little bit with the file system this year. Users have been doing a lot of Conda stuff on it, and it's really caused havoc when you run at scale. It's got a bunch of issues with all tasks, basically always trying to access and write to the same file, and that with Lustre, that always seems to cause problems. And inevitably, we have still struggled and tried to educate users on proper use of Conda. So, and of course, Ranch is our 100 petabyte tape archive library from Quantum. That's still in production. We are looking and hoping to replace that this year as part of LCCF. We do have designs. We're looking at potentially deploying a tape subsystem of an exabyte that could grow to an exabyte in size over the next 10 years, basically. But unfortunately, we haven't been able to finalize the plans for that. I have to admit, a lot of our LCCF work has been put on pause due to the NSF funding and issues and halts and chaos that's generally been produced. But we're now starting to move forward. They're starting to finally let us move forward with some of the LCCF purchasing and plans. So. All right, so let me jump into Frontera. So the highlight of Frontera, of course, here's the total number of compute nodes. We got well over 8,400 compute nodes total in the system. Again, these are all Cascade Lake Intel processors, 56 cores per node, very, very similarly configured. We're still running our NVDIMM nodes. Those guys who need large memory. I have to admit, we've pretty much reconfigured them. We've done away with all the storage that was on the NVDIMM nodes. Users didn't really use them as storage. They really want that 6 terabytes of RAM for for applications and processes that they can't necessarily parallelize and distribute across lots of nodes. And so we have reconfigured those so that they're pretty much just running as memory and not storage anymore. We still have all of our RTX nodes, so 360 RTXs. Those are slowly dying. Again, this hardware is more than 6 years old. In fact, I was deploying it 6 years ago right now. It is pretty long in the tooth, and it's been really, really heavily utilized. Those commodity RTX 5000 cards are probably never designed to be driven like they were by our users. And so we are starting to see some failure rates on them, and we're starting to basically cannibalize spare parts to keep as much of the system up and running as we can. I think we've only lost about 4 of the GRC nodes, but still that's 16 GPUs that we're down right now. So it is all HDR InfiniBand interconnect, still running our 18K DDN storage for, it's all Lustre based. The IME storage, we still have half of that configured for IME, and our main problem with IME is we just haven't really had a lot of users that can take advantage of it and get the performance that it should deliver. But we do have a handful of cases that it still works very well for. What we're doing now is we're actually reconfiguring the other half of the servers to be different flash file systems. We evaluated Weka on it. We tinkered with, just deploying Lustre straight onto it. We've actually just seen if there's some way we could reuse that flash storage and still get some benefits from it, and also explore, potentially other non-standard, file system configurations. Again, Frontera has access to both Stockyard 2 and the Ranch system. So just to show you the nodes, again, these are the direct liquid cooled nodes. 75% of the cooling is the direct liquid cooling to the blocks. We still have, about 25% of the cooling is needed to cool the rest of the memory and the InfiniBand card and motherboard. So we do have chilled doors on the backs of these racks. But again, 75% of the cooling is provided by the direct liquid cooling. We did have a lot of issues with the direct liquid cooling, reported over the years about the mini leaks and everything. I'm happy to say that since we completed the full block replacement on all 8008 servers, we've had 0 leaks due to the issues at the cooling blocks that we had previously. I think we've still had a couple of leaks at the connector manifolds, but again, it's not inside the node. Leaks external to the node are tolerable. When they're inside the node and they destroy processors and motherboards, that becomes more challenging to maintain. In terms of the compute node, I mentioned here's the racks. Very dense racks. These are a little bit taller racks. It is interesting. We are seeing that, even the OCP standard is starting to adopt taller racks. So we're probably going to have to get used to a little bit taller racks. For us, it worked out really well to use these 54U racks because we could squeeze enough nodes to be able to get enough ports into each top of rack switch. And again, when we design these systems, a lot of times we figure out how many nodes we can fit in the rack just based on how many nodes we can connect into each switch. In here, we opted for a little bit of oversubscription. We have 44 nodes plugged into each switch, which means that that's 22 of the ports, and we have 18 uplinks. So you notice here that 44 of the nodes run at 100 gigabits and then 18 uplinks at the 200 gigabits. So again, a little bit of oversubscription. Most of our users aren't really impacted by that level of oversubscription. Although if you're doing FFTs or anything that's doing a lot of all-to-all communications, we do see congestion on the fabric in those cases, especially when we're running on all 8,000 nodes with one single application. We definitely have seen that occur. The problem is most of that is very small messages, and so it's not a huge performance impact. We're not seeing that congestion drag down the performance of the system at scale. We are, in fact, in the next future systems, we have tried to architect with full non-blocking fabrics just to avoid that. Here's the layout of the system. Again, for those of you who haven't been able to tour up here and see the facility, we're able to get all 91 racks of the liquid cooling into 3 rows of where the old Stampede 1 was located. The old Stampede 2 is just kind of north of this layout. In fact, here's part of those racks are shown in the upper left corner of this image. The design, though, was fantastic because we were able to leverage the fact that we put 3 CDUs in each row, and we had 1 cooling loop under the all row, and we only need 2 of those CDUs to be operational to keep everything cool in the row. That has been fantastic in terms of maintenance and operations. We've been able to take them out of production and not impact operations of our users. We've had some leaks at the pumps and some other things where we've had to work on the CDUs, and it has been really convenient to be able to take one out of production in a row and do maintenance work on it and not have to have impact on the rest of the computes. the downside is you know, the densities of the racks that we're seeing coming, especially with the GPU and AI focused racks. You know, it's going to be hard to design with cooling loop redundancy and CDU redundancy in mind. You know, it's literally, you know, it's going to be like one CDU feeding 4 or 5 racks, and you know, we've talked to the different vendors, and you know, to build the loops and cooling for in the secondary flow, you know, the flow rate you have to get, the pipes are going to just have to be too big, and it gets a little bit more challenging to handle redundancy. But I have to admit, it's been really nice to be able to have those as redundant in the rows. So you do see also the 6-core switches. So these are the big Mellanox core switches. I think these are the last generation of their director class switches. I think moving forward, they're moving to the, you know, 4U and more top of rack type switches. So I am sad. I've gone through multiple generations of those big director class switches. You know, going back even to Ranger time frame, and they've been pretty useful and nice to have everything organized and connected together and not have to worry about the multiple layers of fabric. But with the switch radixes going up as much as they are, you're just not going to need as many switches at the spine of your designs. In fact, most of the designs we're looking at now for future systems have far fewer spine switches than what we've had to deploy on Frontera. So, all right. So quick updates for this year. You know, we're still running CentOS 7.9 that we installed in 2021. It's been stable, it's been robust. We've been super happy with it. We're still watching Red Hat for any security patches and any updates. There are a few updates that have been installed on it. You know, we did talk to our users at the last user group meeting and said, hey, are you willing for us to take a, you know, extended outage to do a Rocky 9 upgrade or something like that? And they're like, well, it's not necessary, so if you can avoid it. So we debated it, and for now we're going to continue to run CentOS 7.9 unless we stumble into some big gotcha or security issue that we absolutely need to upgrade. So but you know, it's been stable. We haven't had to take, you know, a whole lot of maintenances, and it's been very productive. So again, we still haven't been upgrading the software though. We still upgrade the Intel 1 API compilers and still try to keep up with the software stack. And same with the Lustre and Exascaler updates. We continue to roll versions out. In fact, we just updated our DDN client on the compute nodes so we can do some proof of concept testing with their compression. So maybe next year you can pick Hio or John DeSantis's brain about experiences on that. So. The other big thing is that we're still supporting the Texas Scale weeks. We had 4 last year, where we basically take the entire system down for a full week and let individual groups take advantage of either the full system, all 8,300 nodes, or two at 4096 scale. Again, a lot of this is to push the boundaries of what they can do. We have one group that basically has decided that they only want to run that one day in Texas Scale. They can produce enough data on all 8,000 nodes that they can spend basically 3 months processing it after that, and then still and then be ready for the next Texas Scale to produce the next round of data for their processing. So we're over 7 million jobs on the system. You know, as I mentioned, we're just right now keeping the system stable, available users, no real major updates planned. We do continually to add third-party packages. Users still request software, still want new versions of stuff. And so, you know, we've steadily grown our install image over the 5 years of operation we've already gone through. So, but anyway, it's been a great productive system, been real happy with Frontera. You know, we are still having some ongoing challenges, you know, keeping up with the hardware. ECCs have been, you know, we got, I can't remember the counts, like 200,000 DIMMs on the system. So, you know, number of DIMMs we've had to replace is still just a huge number, and that's really the one thing that we struggle keeping up with. We are having to cannibalize nodes. They're not under warranty anymore. We let the warranty expire after the 5th year on the compute nodes themselves. Kept the storage and InfiniBand fabric and network gear all under warranty, but not the computes. And so we started cannibalizing the compute nodes and keeping everything we can up and running. So, you know, users have been happy. It's been a great productive system. We continue to hopefully be able to operate it and keep it running for the next year until Horizon comes online. So, um, as I mentioned, we did stumble into one gotcha this year in that we did a Lustre client update that has triggered some stability issues with actually Stockyard, and we're working with Didi and hopefully to resolve those right now. So, um, all right, real quick, I'll stop here. Keith, any questions in the room about Frontera? Any things, topics, discussion?
Russell, can you tell us more about the Conda issue you have with Lustre?
So, all right. So here's the thing. You know, we have thousands of users on our systems, right? So, and a lot of them are very big Python friends. So, and you know, it's very simple. I have to admit, Conda and Python makes this way too easy. So what ends up happening is users do a Conda install of some package, you know, install into their own local location. That's fine by us. But what Conda or Anaconda does, I don't know which one it is actually, but all I know is that what it does, it modifies their .bashrc file, and it puts a little stub in there that does a conda activate and some directory location, which users, because it's convenient, they put it on our Stockyard work file system. Again, these packages aren't very big. They get a terabyte of quota on work. So, you know, they can install a lot of their software and input files and things there. So what ends up happening though is it modifies the bashrc and puts this conda activate. The conda activate process tickles one file in that file system, and what ends up happening is when they launch, let's say hundreds of jobs on 1,000 nodes or so, it ends up basically all trying to access and write to this one file, and either basically grinds the application to a halt because all the locks that have to happen, or it will overload the individual storage server just with requests and drag it to a halt, which then of course drags everything in terms of your Lustre file system down. And anything trying to access that is super slow to respond. So so we have tried to work around it. Our main annoyance is they should not be modifying the bashrc file. They should modify that .login or the .profile, bash profile. If they modified that, that's only initiated on login scripts. It's not initiated when you launch shells on the back end. But the bashrc file is every shell, it gets read. And so we have put a little, you know, we've gone through and modified the bashrc for what users normally get to try to skip if it sees that it's a conda and you're on a compute node. But the problem is users can modify their bashrc, and if they have an old one, they don't have anything new, then they can fall into this trap. So just be aware of it. Again, it's mainly an issue when you start to launch on hundreds of nodes and thousands of tasks. It's just, yeah, the file system can't handle it. Funny thing is, our VAST file system hasn't struggled with that issue yet. So we'll see if it pops up yet or not. So that answer your question, Russell?
I think it did.
Okay.
Yeah, I know that you guys changed out the cooling blocks, so you're not really 5 years into the water chemistry. But are you guys sampling the water chemistry and maybe looking at adding boosters or flushing filling? Your PGW25, I guess, but you know, what can you tell us a little bit about, you know, from a scale perspective, what you're seeing on water chemistry and its expected life?
Yeah. So absolutely. In fact, that's something we've been trying to keep a close eye on, is our PG25. So we do have a contract with a local company that Cool IT had hired to, and they take samples every 3 months. They have not told us that they've had any issues with it. They are still sampling and doing the chemistry. I haven't seen any particular breakdown of the fluids or anything, but it's something that we're hoping they will let us know if it's an issue. But I haven't seen anything with the PG25 or any reports as of yet. So it still seems to be surviving even after, you know, we're approaching 6 years of having that fluid in the secondary cooling loops as of now.
Do you recommend pulling out a heatsink or as a node goes down and opening it up and checking for fouling or anything like that?
If yeah, I mean, if we have a node go down and we have to pull it, we absolutely go ahead and check the cooling block to make sure that there hasn't been any new leaks. And you know, just because we're a little gun shy on that now and have gotten burned. But you know, the good news is I'm almost positive we have seen zero additional leaks inside the node since the cooling blocks have all been replaced. But again, you know, we're only like 2 years into that after all the cooling blocks are done. And it took us at least 2.5 years before we really started seeing the leaks in the last round. So.
Any other questions? Yes. Tommy, what has life been like with the end of support for CentOS 7.9?
Yeah, it's been a concern. You know, we are watching Red Hat. We do have Red Hat licenses, and so we are watching what they're doing with the 7.9. If we see they have any security patches, we'll go ahead and patch our kernel. There have still been a few little updates to some of the packages. We were a little surprised that they were still updating some things, but the repos still seem to be getting updated. My main concern is a security vulnerability, but you know, I can sleep a little bit better knowing that, you know, everybody that has to access the system has to use multi-factor authentication, and that's really basically cut down our external security incidents on systems like Frontera to zero. So even if there is a vulnerability out there in the current 7.9 stack, at least with our MFA, we're a little bit more protected on that. So, but it's something that guys are watching pretty closely. It's one of those trade-offs. I mean, it would probably take us 3 or 4 days of downtime to do a full upgrade of everything to Rocky 9 and get it hammered out and ensure that launching jobs on, you know, all 8,000 nodes are going to work. And it's going to be, it would be a lot of work. And it's not sure we'd get a lot of return from an upgrade right now.
I
right.
think that's the questions we have now.
Okay, let me jump on to Lone Star 6 then. So Lone Star 6 actually just completed its 3rd full year of production at the end of December. 2.2 million jobs run on the system so far. I think on the previous updates, I'd mentioned that we had kind of added this concept of virtual compute nodes on the system. One of the things we struggle with on a system like Lone Star 6 is, you know, they got the AMD 64 core parts, and it's 128 cores per node, and a lot of our smaller Lone Star users and local UT users, they don't run at the scale like people do on Frontera, and a lot of them just need small 16 core threaded, you know, Python scripts that they're running. And so we had a lot of demand for smaller node instances so they wouldn't get charged for a whole node. And so we basically rolled out this instance where we basically took a lightweight KVM on every node and carved each node into 7 16-core instances. We tried 8, and 8, if you're running on all 8 16-core instances, that actually just overwhelmed the node a little bit too much and impacted performance. So we opted to just do 7. And each one of these instances actually has a full hard drive for it. So that means that we can, you know, still have a local temp image for the users that's the full size, like a regular compute node. So, and we can put our full stack on there because we have enough space. We also adopted that same thing to our GPU nodes. So we have you know, 3 physical GPUs per our GPU nodes, and we have 80 of those nodes. So we've taken 4 of those nodes and carved them up to 3 virtual images per node, 1 per GPU. We did try to use MIG. MIG is the multi-instance GPU tool that NVIDIA is working on. Basically, it can let you run 7 virtual instances on 1 GPU. We tried to do it in our environment. Unfortunately, one of the challenges is we like to reset the GPUs between jobs just to clear them off and make sure that they're healthy and robust. And if there's users sharing a GPU with MIG, you can't necessarily reset them. And you know, it was honestly, we just didn't feel it was quite production ready yet. Now that was several months ago. I mean, that was at least 6 months ago when we started working on this. I know that they've improved it. But you know, this is something that we're still watching and just haven't rolled out yet. But it's something we think we could take advantage of, especially for classes where, you know, an individual trainee in some you know, training class or in a university class, they don't need a whole GPU. They just need a little portion of a GPU to tinker with. So we'd really like to be able to roll MIG out so we could support more users and not have to sacrifice as many nodes to support a training class. And so, and we still have our 8 nodes that are the Genoa processors. These we actually installed the H100s in, because of the power in the PCI generation, we needed the newer AMD systems to be able to run that. And we have encountered some issues with the power cords on these nodes. The H100s draw a lot of power. You may have seen people reporting the new GPUs melting cords in the desktops and so forth with gamers. Well, we had a similar set of instances with our initial cords that we'd gotten from Dell for these H100s. They've since given us new cables that are a little beefier and can handle the power that these GPUs draw now. So, again, here's the compute nodes. The whole system, we have about 624 total nodes. We all chose basically an identical processor configuration on the nodes, and it's just basically a mix of whether they're liquid immersion nodes, half U, air-cooled nodes at 1U, which makes the bulk of what's installed in the air-cooled racks, or the 2U nodes that have GPUs or other they're configured for other accelerators as well. But we tried to keep basically Milan processors across the board, kept everything identical in terms of the memory configurations to make it a little bit easier for the users to use each of the systems. And again, I mentioned the 80 nodes with the 240 A100 GPUs in those nodes. It's all Mellanox HDR InfiniBand. Each rack is actually full non-blocking. We have the 40-port switches, and then we have 16 core switches in each of the that each of the top of racks connects to. So again, we have a mix of air-cooled and some supporting the immersion, and of course our Ethernet that we're always surprised. We are starting to move on. One thing that we are starting to move away from. We had been doing GigE for our management network, but the cost of 25 gigabit now is getting to a point where we're pretty much putting 25 gigabit for all of our backend stuff now. For shared with data and management, so we still will SSH over the Ethernet port. The compute racks are basically, here's the air-cooled racks. What we did is we put the really high-power GPU nodes in the bottom of each of these racks. So if you notice, there's 4 2U nodes at the bottom, and then we have a mix of 20 1U nodes in each of the rack. So 24 total nodes. That's about 25 kilowatts of total power. That's about as much as we could do in that old air-cooled portion of the room. It is in the older portion of the room where we still have 208 volt power and underfloor and cooling and a little bit of in-row cooling around the systems as well. So again, we also have the immersion racks. These are the racks when they're installed. We've basically configured each of our racks. We expected them to be about 65 kilowatts of power when we were doing the power rating. It turns out the AMD nodes actually run at a little bit higher power than they had originally anticipated, and we're actually measuring about 70 kilowatts in each of the racks. So here you can see the 84 servers mounted in one of the tanks. And then on the right is after the cabling. You'll see the switches are mounted on the fronts of the racks here. There's an anecdotal story about those switches. They are mounted upside down because they have heat pipes in them. We initially had mounted them vertically, and as we started plugging in cables, they kept overheating. But when we'd feel the air blowing out, it was not hot, and we were like puzzled. We had a switch that had been damaged that we took apart, and sure enough, we noticed the heat pipe in it. So all we had to do was flip the switch over, and now they stay perfectly cool. There was nothing in the manual about not mounting them vertically. My understanding is the NDR switch manual has in there that you're not allowed to mount them vertically. So just be aware that the rules may have changed on mounting of your InfiniBand switches. So, but because of that, you'll notice that all the fiber basically is coming off the bottom of each of these switches. And then there's one big challenge with these tanks in that there's one penetration in the very middle of the tanks, and all of your fiber cables and all your power cables that feed everything must come through that penetration. because it's what captures any oil that might leak out of the tank or drip out, gets captured at the bottom, and you don't want it to leak out of the bottom capture. That's why you have this big penetration in the middle. And so that was a bit challenging with the deployment. And then once everything was done, we wrapped it up, made it look nice. I know Shell has a bunch of these that look pretty good. And that is one advantage to the tanks. You can at least put some nice little graphics on it. So, all right. A few other little items about the system. It's BGFS. This was actually our very first production BGFS file system. We've been pretty happy with it. I will say it is not as performant as Luster. You just won't get the headline speeds, but it's been more robust and more reliable. We haven't had users been able to really make it fall over. We can certainly cause users to overwhelm individual servers, and we'll track that down and find them. But you know, they don't necessarily crash or get into a state where they just get to a point that, you know, you have to do a failover or you have to do something to recover the server when they just get stuck like a Luster server might. So we did stumble into one kind of big gotcha on the storage subsystem. You know, we've tried to enable most of the POSIX stuff. And we did find that if you enable ACLs, you know, access control layers on this file system on BGFS, you will take a huge performance hit. You absolutely want to make sure you're going to understand the loss of performance you get if you do enable ACLs on the file system. We've been lucky enough, you know, we don't put any protected data, we don't put anything of real critical nature on Scratch or Home for our file systems, and so so we were able to disable the ACLs, but you know, some of our users were using them, and so we had to go back and make sure that they understood that they were disabled. So, but anyway, just a caveat for those of you who might be testing with BGFS. All right, again, we have a huge software stack. This is very similar to everything we've deployed on all of our production systems. You see a similar setup for Frontera. You know, the big thing about Lone Star 6, it's still Rocky 8. We are still sticking with Rocky 8. I think we do plans to upgrade to Rocky 8.8 soon. We still have the Intel compilers on it. They still seem to be great for even the x86 AMD processors. And, you know, we do support a couple of different compilers. Try to support multiple MPI libraries depending on what users want to use. And the big one, of course, on the right is we're starting to do a lot more containers. See people use containers, especially for AI applications and so forth. And there are a lot of users who are, you know, the GPU nodes on Lone Star 6, those A100s are in very high demand. And definitely the longest queue wait times on the system. And a lot of that is AI research. All right. Again, I mentioned a lot of the compiler stacks. I'm going to get through this, run a little bit behind. Again, LMOD, I highly recommend if you're deploying systems, module environments make your users' lives a lot easier. We implement LMOD, which is what we consider, we call module on steroids. Module was originally developed, I think, way back when on Cray. But you know, one of the things we wanted to do is try to make it a little bit more user-proof. We get a lot of novice users every year. About a quarter of our users are new, and you know, new graduate students. They haven't seen command lines. They don't understand HPC. You know, they may be used to Windows desktop environments, and so we try to make their life as much easier so that they can, you know, log in, load modules, so that they get all the software pieces that they need. Set up all the dependencies and hierarchies so that, you know, if you load this compiler, you get access to these software packages that are built with that compiler or MPI library. I know it's got a huge community. There's a lot of people who really like this setup. And if you can make sure your HPC administrators and everything can adopt this when they're building application packages, it makes system administrator deployment a lot easier. You know, for us, what we tell our HPC folks is you go build the application, put it into a couple of RPMs, 1 RPM of the application, 1 RPM of the modules, make them relocatable if at all possible, so we can be flexible if we install them on the local disk or install them into a shared location. And because we have the module environment set up, users, you know, as soon as a package is on the system, they can just do module load and get access to it. And we can make sure that they don't have, you know, conflicts or dependency issues all based on the module stack. So again, highly recommend to make administrators' lives a lot easier. Um, Lone Star 6, like I said, been great production system too. The per core performance is not quite as good as, our current Frontera and Stampede 3 Xeon nodes. But if you can use all 128 cores on a node, the nodes, individual nodes certainly outperform Frontera and are very competitive even with the Sapphire Rapids nodes on Stampede 3. So we do have expansion plans. In fact, we already have people asking if they can contribute to the cluster. We are looking at buying some potential new nodes. I do try, whenever I build a system like Lone Star 6, I try to build fabric and power and cooling infrastructure in such a way that I can continue to add racks to it. I think I may have mentioned in previous talks that we did have a Giga IO composable infrastructure as part of Lone Star 6. We've actually given that over to the cloud team. They're using it on Chameleon now. For us, it just didn't work very well with production environments. Again, it was a good little test tinkering and everything, but from an operational point of view, it was a little more of a headache. And so we figured it was a little bit better for our test bed environment on Chameleon. So with users still demand a lot of the small partition. That's also a queue that also tends to have a long wait time. But one of the things we need to do is we actually got to get more hard drives to put in the compute node so that we can install more virtual machines. And I think I mentioned this last discussion, but be careful with older MPI versions. They may not let you run 128 MPI tasks per node. So, but again, I think that issue's been resolved with all the latest Intel 1 API versions. So, all right, that's Lone Star 6. I'll stop here if there are any quick questions about Lone Star 6. Again, it's been in operation for a little over 3 years. We plan to run it at least 2 more years. We're getting about 5 years, 6 years of life out of the current systems, just because the infrastructure costs and upfront costs are getting pretty high.
Johnny?
Any questions? Yeah. We have not tested that yet. In fact, actually, the guys are testing that on Vista right now, which is our Grace Hopper system, and we're hoping to be able to do that on that. No, we've been, yeah, we just haven't had a chance to really tinker with it as of yet. But I know NVIDIA's, I think, asking us to. Yeah. Hey, keep us in the loop, or not me, but keep the TACC folks in the loop about your experiences, because we try to tackle a lot of new stuff, but man, it's hard to do everything. Yeah, so I actually have some updates of that on the Stampede 3 and Vista slides, but no, we have not seen any issues with VAST, and any of the problems that we normally would see would grind our Lustre file system to a halt. Not seeing the Conda issues. We're not sure if it's just not proliferating as much, and we don't quite have as many nodes on Stampede 3 and Vista as we do on like Frontera. So users may not be, running that many tasks to cause the Conda issues on the VAST hardware as of yet. But we have been tinkering with the large scale MPI IOs. There is some tuning you need to do if you're doing MPI IO. You certainly do not want to use NFS settings. It will certainly serialize most of your IO. I think with Romeo or one of the MPIO settings, if you set it to the UFS, the Universal File System, you will get decent performance. And we do have some applications that are doing a single file MPIO from 512 tasks on Grace Hopper, and they seem to be writing IO at pretty good rates. And we're still working with the VAST team. We did expand our VAST a couple of times, have done a couple of upgrades. We did have a user tickle a couple of bugs we stumbled into with VAST. We also found out a user could create 500 million files in the span of about a week on our VAST file system, which we didn't stumble into until we tried to purge it, and it ran the node that runs the purge out of memory because it was trying to build a list for the one user. So yeah. Unfortunately, you can let the users go crazy too if they get access to VAST. So we're trying to rein that in right now. So.
Jonathan?
So you mentioned that you had performance problems with ACLs on BGFS, and I'm curious, one, if you have more information about the source of that, if you spoke with ThinkPark or looked at it to see why that's happening, and two, is that unique to BGFS, or are you able to use facults with Lustre file systems? I haven't done that.
Yeah, no, you can use ACLs with Luster, and it doesn't take as a huge of a performance hit. But we go back to Think Park. I'm pretty sure we ran it through Dell because our BGFS support is actually through Dell. So I'm pretty sure they ran it up the chain through Dell and let them know. And I think it was just it may be a limitation with the MDS hardware we have is just not as capable as it could be to be able to support ACLs. But I know it was just way too much of a performance hit for us. And you know, maybe with other hardware, you may not see as much of an impact.
Yeah, I only ask because I've seen very specific, not performance, but storage allocation stuff depending on how your MDSs are aligned. So I'd be interested to look more into it.
Kevin?
Okay. I think I heard that. You were asking if it is server issue or best practice. Um, we actually started doing it because we noticed that you can't always clean up all the memory and all the stuff that users do on the GPUs. Sometimes there's just some cruft on there left over. We don't know what it is with the driver or something. But you know, one of the things we've have done in the past is since we do exclusive usage of the nodes or exclusive usage of an individual GPU, we can just reset that one GPU or reset all three GPUs on Lone Star 6. It just seemed to work really good for us and ensure that everything's healthy and robust. Again, you know, our goal is to make sure that when the user lands on a node, it's as clean and performant as possible. And you know, I don't know if it buys us a whole lot now. I think early on when we had early drivers and early CUDA stuff, I think there were certainly memory leaks and other things that were happening that we needed to clean up from. It may not be as bad now. We are doing this on our Grace Hoppers too. We still reset that Hopper GPU after every job on Vista, and it has stumbled into we stumbled into some gotchas, and it was important now that we do it on Vista, and I have a slide on that coming up. So we're continuing to do it. I don't know if it's a best practice, but it is a sacrifice. You do spend, I don't know, 30 seconds, 45 seconds, maybe a minute to reset the GPU and have it come back. I mean, you know, we're willing to sacrifice that. Most jobs run 48 hours at least, and you know, a couple of minutes to ensure a node is nice and healthy and clean for the next user, I think is worth the time.
Sean?
I'm sorry, could you repeat that one, Keith? I couldn't hear that one.
What scheduler are you using?
Oh, it's Slurm. Everything is Slurm. So we have moved everything to Slurm. We're running, in fact, we just upgraded Stampede 3 to the very latest Slurm 2310 something, or I don't know what they're up to now, or 2024 something. But yeah, it's Slurm everywhere. It's just work for us. Yeah. We did try to buy support from them at one point, but we've been able to run without it. So. So not with Elmont. So here's the problem with Conda. There's like 8 gazillion packages out there, and we can't support every combination that users want. And so, you know, the nice thing about Conda, what it lets users do is pick and choose the things that they want to install into their own environment. The bad thing is it doesn't take into account overall shared system environments. You know, it was designed for desktops. You know, or working on your laptop or something. So it wasn't designed for big, large HPC environments.
I think that's it.
Okay. All right. Let me accelerate a little bit here, get into Stampede. So, all right. So I know over the years I've talked about Stampede 1, Stampede 2. You know, we back in 2023 timeframe, NSF put out another solicitation for systems. And we pitched a Stampede 3 system to be deployed in late 2024. Basically to continue to support the wide range of Exceed and Now Access users that need a large, you know, CPU-based applications. You know, we do a lot of emergency response and priority response support for, you know, the community on systems like Stampede. and we wanted to be able to still support those level of activities. And both systems were in huge, high demand, well oversubscribed in terms of the user requests, and delivered a lot of science over our life. And so we wanted to continue to build upon that. And so basically our goal was really to take our existing Stampede 2 hardware, reuse what we could and what we felt comfortable reusing, because most of that hardware is out of warranty. Try to provide an environment very similar to what Stampede 2 was, provide minimal interruption. In fact, we kept Stampede 2 running until we had Stampede 3 up and in production, or at least a portion of it. And then also provide some AI ML resources that may not be available at other systems. And since we already had, AMD, NVIDIA, and Intel, we wanted to kind of complement the hardware that we already had in Frontera and Lone Star 6 and what was coming in Vista. So we proposed Stampede 3. Basically, the goal here was add Intel Sapphire Rapids nodes. We added about now we're up to 660 Sapphire Rapids nodes. I think that's right. We had some AI-focused GPU nodes, so we do have some 20 Ponte Vecchio nodes in the system with 80 of the GPUs. We also wanted to support next generation 400 gigabit fabric, so our plan was to install it as soon as it became available. Now the plan is to just install that later this year, assuming it still comes available. And the big thing on Stampede 3 is our first real vast large-scale production system. We had done Lustre in the past. We still have access to the work Lustre file system on Stampede 3, but we wanted to replace the Scratch file system with VAST, and again make sure that we were happy with it, so that we could look at deploy it on for LCCF in the Horizon timeframe. So. The compute hardware, we still reused 1,064 of our C6420 nodes. I still have probably 300 of these nodes as spares that are, they're sitting in there unplugged. We just didn't have enough connectivity and power to be able to run all the old nodes. And again, we wanted to make sure we had plenty of spares for the life of the system. We reused our 224 Ice Lake nodes. These are the 40 core per node, 40 cores per socket, 80 cores per node. Good Ice Lake processors. Nice thing about these nodes, they had a little bit more memory than the standard Skylake nodes. And so users who need a little bit more per core can get access to that system. And then of course we have the 560 dual Sapphire Rapids nodes, 112 cores per node, 128 gigabytes of HBM. We did not put any DIMMs in these nodes. Based on prior experience with Knights Landing on Stampede 2, we had opted to not do additional DIMMs for HBM. When we looked at all the applications, the vast majority of our applications actually only use less than 1 gig per core. And so since we could support about more than 80% of the applications with the HBM memory, and the complications that you get into if you're using HBM as cache over DIMMs, we opted just to not put any DIMMs. Plus, it saved a lot of money. DIMMs are pretty expensive. So that's why we ended up doing that on these Sapphire Rapids nodes. Again, I mentioned the Ponte Vecchio nodes. These are the XE9640 nodes, liquid cooled. Again, all the Sapphire Rapids and all the Ponte Vecchio nodes are liquid cooled nodes on the system. So we're actually still in process on this expansion. We're adding 56 more Sapphire Rapids nodes to the system. But the big thing on this one, we're adding some more liquid cooled GPU nodes. Intel, when we deployed the Ponte Vecchios at the time, Intel was committed to that. They've since discontinued the Ponte Vecchio line. So we opted to go with more of an H100 environment. Again, this is really to support NAIR, which is the National AI Research Resources infrastructure. And basically this is the US government pushing into AI and trying to support more AI researchers. I have to say, we're having a little challenge right now. The nodes are here, the racks are here, everything's here, except for the cooling manifolds and the PDUs. This is the one downside with what AI is doing. They are stealing all of our hardware. We have yet to be able to get our PDUs delivered. And apparently agencies keep jumping in the line ahead of us. So we're still waiting to get those PDUs. I did hear that the cooling manifolds did finally ship, but I have to say that the guys purchasing all the gear to support AI, boy, they have really put a damper on our market. They have certainly consumed everything that we need for infrastructure wise. Heck, I even heard Elon's building his own transformers at the Gigafactory here in Austin, just because he can't get transformers for his XAI data centers that they're building out. So we also did add additional capacity to our VAST hardware. I mentioned, we've been super happy with VAST. We did the upgrade live. We rolled out the expansion. It worked in the background. Took a little bit of degradation in overall peak performance while it was doing the rebuild and in the background. But we've added D nodes, we've added C nodes, we've added, expanded the system. We've done 3 rolling upgrades on it while Stampede 3's been in production, and have had 0 downtime on the VAST hardware. We did have one little issue that was a gotcha. One of our switches was misbehaving, and we weren't getting indication that it was misbehaving. And unfortunately, when it did start misbehaving, it did degrade performance, and that's how we ended up actually noticing the issue. Good news is VAST has added checks now so that they can find and detect if a switch gets into this state. It turns out that one of the configurations for the lag was not set up right on one of the switches, and that was causing it to have the issues. So, but they've added checks now and can detect that. So, but again, been super happy with it so far. So yeah, so we're over our first full year of operations. Again, this is the Stampede 3 tends to be more of a throughput system than a big production system like Frontera. So we're already over 1.5 million jobs. Just in the 1 year, we produced about 25 petabytes of data on the VAST file system so far. And we've already purged more than 15. And so, we have put it through its ringers, man. The guys do a great job of producing a lot of data and producing a lot of inodes. And knock on wood, I've been super happy that haven't had any downtimes, or I haven't had to wake up at 3 a.m. due to a call to fix a file system issue. So that's something I'm not going to miss once I retire. So the Skylake nodes are still in super heavy demand. The users just love those Skylake nodes. We try to convince them to use the Ice Lake and Sapphire Rapids nodes, but man, they're willing to wait hours in the queue to even though when Ice Lake nodes might be available, and still, yeah, they just really like the Skylake nodes. And we are actually, I admit, I put in, we haven't seen as much uptake, but we are starting to see a lot more ramp up on the Sapphire Rapids nodes, because users have figured out if they have memory bandwidth limitations on their application, they can take advantage of only having 1 gig per core, that they really can get great performance out of those Sapphire Rapids nodes. And so we are starting to see a little bit more demand up, but the queue weights on it are probably the lowest on Stampede 3 compared to the Skylakes or the Ice Lakes. So. All right, Keith, let me stop there. Quick questions on, and this is the base level VAST configuration we did for the systems, but quick questions before I jump into Vista, and I'll finish up with Vista real quick.
Tommy, what's your purge policy on Scratch?
So for us, we basically, I think right now we're purging any file that has not been accessed in 120 days. On Frontera, we're actually purging about 60 days right now, just because we can't really keep up with the capacity. But right now on the VAST, I think we're at about 120 days right now. But as users continue to produce data, we'll have to shrink that window down. We are a couple of other things on the VAST. We are using the snapshotting on the home portion of the VAST file system. Makes backups a little nicer. We used to do nightly backups incrementally and weekly full backups. We still do the weekly full backups onto tape, but now we use snapshots for a couple of weeks worth of data. So if we need to recover something from home, we don't have to go back and pull it from tape. So I did want to mention that we are using that capability as well. But yeah, we have to basically any file, and again, it has to be accessed. We do look at access times. One little note though, on our logins, we mount the Scratch file system with no A time. So users have to access it on a compute node. So.
think we're good.
And I did have one and the other big thing about VAST that we've been able to take advantage of is they have a data catalog now. Used to on Lustre, we'd have to do a scan and check the 8 times of all the files and then get a whole long list of files and then remove the files. And with the VAST subsystem and being able to use their data catalog and indexing, we get the list of file almost instantaneously on a per user basis. So our purge script actually targets the users consuming the most space first. So we actually rank sort our users by how much they're currently using and really start purging the ones that are using the most first. Happy to share. I can get you access to the admin who writes those tools and uses the data catalog if you have further questions on that. His name is Nick Lewis.
I think we're good, Tommy. Go ahead.
All right. On to Vista. All right. So I'm not sure. I don't remember how much DeSantis mentioned about Vista last year. He is the lead sysadmin on Vista. But this is where our very first foray into a large ARM-based cluster. We've done some small ARM systems and some small ARM testing previously, but this is kind of our big first foray. So we ended up getting 260 of the Grace compute nodes. These are the dual socket ARM processors. These nodes are the 240 gigabytes per socket, 480 gigabytes per node. With NDR, it's all NDR 200 gigabit fabric. Again, we went 200 gigabit on these nodes because we didn't need all the bandwidth to the Grace nodes. Then we got 600 Grace Hopper nodes. Now, 300 of the nodes were purchased through NSF and the Vista grant from NSF. But 300 nodes were also purchased by UT here in Austin to support the AI researchers on campus. These Grace Hopper nodes have, again, they're really 240 gigabytes of CPU memory and 96 gigabytes of GPU memory. We went NDR 400 to these nodes, so they are the full 400 gigabit bandwidth on the NDR. And we did a full non-blocking NDR InfiniBand interconnect with 16 core switches. So each rack has 32 GPU nodes in it. That's about as much as we could get in the racks for power and cooling because they are air cooled. And because we have 32 nodes, we have 32 uplinks per top of rack switch, so 2 to each core switch. And we do have ability, again, I have some spare ports on the core switches available for expansion. Again, we're using VAST for our home and scratch file systems on Vista as well. And really the big thing from us is the CPU and the GPUs are really exceeding our performance expectations. Every piece of software we have built from scratch has been able to compile and run on the ARM processor. Libraries and most of the device drivers are rapidly evolving though, and it has been a bit challenging to keep up. We have stumbled into bugs. Brand new hardware, brand new technology. Again, we expect that we're going to stumble into some of these gotchas. And again, the good thing is hopefully we find them first, and then when y'all get the hardware, y'all don't have to deal with it. So, again, I got some slide on that coming up. The guys, the CGAI guys, the cognitive generative AI guys down on our campus that got a big chunk of the allocation since that they were one of the groups that purchased part of the nodes. They are really going like gangbusters. They are running hard, and they can really push the GPUs to 600 plus watts. Interestingly enough, the GPUs are capped at about 900 watts, but we have not seen anything push them that hard, other than LinPack. LinPack does push them close to that, but real applications typically under 600 watts. In fact, most are probably in 300 or 400 watt range. And even then, they're getting really good performance at that. This is not Dell hardware that we have. It's actually from Gigabyte. It has been a bit challenging for us to get parts and fix and resolve. Gigabyte is not used to dealing with end customers. They're more suppliers to OEMs. So it has been a bit challenging. I have a new appreciation for Dell and HP and Lenovo hardware and their management boards and everything. Not having just a base BMC is a little bit limiting. BIOS and other updates have been challenging to roll out and keep stable. So just a little caveat there if you do get some Gigabyte hardware. So on the GPU friendly applications, we're really seeing some great speed up. I mean, we're seeing some stuff that's 100x over the RTX nodes on Frontera. and even well outperforming the A100s on Lone Star. So the molecular dynamics codes have been well suited. They work really well on the Grace hoppers. You know, the CPUs are still really competitive. We have one group that has, you know, basically they're saying that the Grace CPUs basically almost competitive with the current Sapphire Rapids nodes, and you know that's great for us because you know they came out about the same time, and we wanted to make sure that you know the ARM processors themselves are going to deliver the performance we want. Now, if you look at performance per watt, they are way better than any of our other processors. Those Sapphire Rapids processors, they are power hungry. And if you go look and do performance based on power for the current applications that our HPC group has been showing, it's been way better than the x86. I think Dan may have shown a slide or two of this during his talk. So, but yeah, it's been a pretty interesting environment, but it hasn't been without its gotchas. We have found that because they use a unified memory for the CPU and GPU, that it does provide some advantages, but it can have some disadvantages too. And one undesirable side effect we had was file caching. So what we noticed is that users, when they're performing a lot of I/O on the node, you know, they're maybe copying some files to temp or just copying some files around, it'll start to buffer. You know, that's been in Linux forever, really. You know, it's smart. It initially buffers onto the CPU memory, but if you actually fill it up, the Linux kernel sees this wonderful GPU memory available over there, and it just starts to fill it up as well. One of the things that we stumbled into on this is this can introduce kernel memory pages that land on the GPU memory that can't be migrated or removed. And the reason we actually stumbled into this is we had some users, again, actually it was the CGAI guys, they would run jobs, and then every once in a while they would get a job fail because it couldn't allocate memory on the GPUs, and we kept scratching our heads going, what's going on here? There's plenty of memory available on the GPU. What's, you know, we're really struggling. But we ended up stumbling into the fact that he was copying a bunch of files. Initially, it was buffering that, spilling over into the GPU memory. Then when he'd go to run his application, it would actually not have enough memory to run. Then once the job finished, it cleared everything out, and we would reset the GPU at the end of the job, and that would end up clearing everything out. But what we end up stumbling into is that you couldn't reset the GPU in some cases because the memory was still in use by the kernel. And that was resulting in system lockups from our point of view. So the good news is because we were resetting the GPU, we were, you know, circumventing some of this issue propagating and continuing to linger. And it you know, let us actually find that, hey, if we can't reset the GPU, something's going on. And that's really how we stumbled into this file caching issue. I know other sites have reported it. I know it's a known problem. The good news is NVIDIA is about to have some fixes for us to work around this. In fact, I think we're testing some beta drivers that they provided. We have used some kernel settings to help alleviate this so that it doesn't try to use the GPU memory for file caching, and can work around this to some extent. But I think the big thing is to have the driver fix the issues and make sure that it doesn't do any file caching onto the GPUs. And NVIDIA's, I think, pretty close to having this resolved. So, all right, I know I ran over a little bit of my time, but just two quick little things. We are doing cooling system evaluations. We still have these ongoing. We do have a Chilldyne deployment on Vista. It's cooling 32 Grace Hopper nodes. And for those of you who might have been at the BOF earlier this week, the ARPA-E group with the Cooler Chips project has funded this activity with Chilldyne. And it's interesting. It's a negative pressure loop. You know, it's a no-leak design. And I have to admit, that's very attractive based on prior experience with cooling systems. You know, if you get any break or leak, it actually sucks the fluid back into the CDU and you don't have anything in your nodes. So we just really started getting this into production. We're collecting data on it right now. Again, we're just trying to see if it's more robust, reliable for the future. And we do have a small ZutaCore two-phase cooling solution in the system. You know, it's working pretty well. It is interesting. One thing we've noticed on our Lone Star 6 AMD nodes that have these ZutaCore two-phase in it, they actually idle at a higher temp than normal. But when we talk to the ZutaCore guys, it turns out that they're idling at about 45 Celsius, whereas our air-cooled nodes will idle about, you know, under 30 or right under 30. It turns out that the two-phase fluid doesn't start boiling off until you get above 45 Celsius. So you don't really start to put any effort into the cooling system until you kind of get above that temperature. But when the processors are running full bore, you know, they're kept below 60 Celsius. Whereas our air-cooled ones, you know, if they're really running hard, they'll hit 90. And so it is interesting to see that, you know, we're seeing less thermal cycling of the CPUs on the ZutaCore hardware. You know, the challenges, I think, is, you know, at large scale, the two-phase cooling loops are a little bit more challenging. I really like the PG25 loops. Those are pretty easy to manage and maintain. And a big, large system with two-phase would certainly be a little bit more challenging to deploy. But they custom cut all the cable, I mean, all the tubing. They had plenty of flexibility inside the nodes to route through the one empty slot that we had available for the cooling, and it's been working pretty well. So, all right. Sorry, Keith, ran a little long, but we started a little late. But
That's no problem.
But
Tom.
anyway.
Tell us
But
about
anyway, great year. Appreciate being able to present and talk to y'all. And hopefully I'll still be involved with the community over the next few years, and certainly won't be a stranger. So,
Tommy, would you hang on and participate in the panel discussion?
yeah, I was planning on participating in the panel. So,
Wonderful,
yeah.
good. Can I ask, what's the fluid used in the two-phase system?
Oh, it's some refrigerant. In fact, I think it's a refrigerant that's banned in Europe right now. But I can't remember which one it is. It's yeah. Go look at the ZutaCore website. They probably have it there.
Okay, thanks.
It's Texas. We're fine.
Any questions for Tommy? Yes, in the back. He asked about the kernel settings that you're using on Grace Hopper until NVIDIA updates the driver.
Yeah, I tell you what, if you can reach out to me or John DeSantis, we can provide that to you. Basically, it's some syscontrol VM settings where you're not as aggressive on it's a couple of NUMA settings basically. And that has alleviated some of the issues and worked around it, but hasn't solved it 100%. Your best bet is going to be to upgrade your drivers when the new NVIDIA drivers come out.
You guys know how to get in touch with John. And Jeremy's got 2 thumbs up, so that's good, Tommy.